In this video, we'll look at exceptions to the octet rule, resonance, and bond order. So first, let's draw the Lewis structure that obeys the octet rule for PO43- and assign the formal charges. If you go through and do this, phosphorus has 5, each of the 4 oxygens have 6, and then we have our 3 bonus electrons from the minus charge, giving us a total of 32 valence electrons. And so if we just divide this around the 4 atoms, so there's a phosphorus and the 4, we could see this would have 32, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that's used the 32 electrons. And if we're doing the formal charges, the phosphorus wants 5. It has 1, 2, 3, 4, so that's a +1. And all of these oxygens, they want 6, but they have 1, 2, 3, 4, 5, 6, 7. So all the oxygens are -1. This is okay because all of these charges add up to -3, which is the charge for the phosphate ion. And so this is a Lewis structure that obeys the octet rule for phosphate. So despite obeying the rule, you'll notice that there's an awful lot of charges on this atom. And remember, our most important formal charge rule was to try to get them all equal to 0. Well, it turns out that if we ignore the octet rule, we can draw a structure for phosphate that minimizes the formal charge. And it looks something like this. So if we get rid of that lone pair and make a double bond to the phosphorus, we now have 3 -1s, which is about as low as we can get for a 3- ion. And now phosphorus and this top oxygen both have a formal charge of 0, which is better in terms of formal charge. But of course this violates the octet rule. However, that actually doesn't matter. Atoms in the 3rd row of the periodic table and below, so actually most of the periodic table can have more than 8 electrons. So remember, period 1 is just hydrogen and helium. Those have 2. Period 2 has to follow the octet rule, but 3 or higher can have 8 or more. So really, the octet rule is kind of just an octet guideline, and it actually only is a rule for period 2. Now, the reason we stress it so much is most of these period 2 elements are really important for organic chemistry. So most of the things that we see in biology will actually follow the octet rule. But for all the things we might encounter in Gen Chem, if it's in period 3 or higher, it can actually violate the octet rule in order to minimize the formal charge. And we see this a lot in the oxyanions, where the central atom is in period 3 or higher. And since we minimize the formal charges and period 3 is allowed to violate the octet rule, this will be the more favorable structure. Let's look at the Lewis structure for SF6. So we can do this and actually get species with even more than 4 things around them. So if we draw SF6, this is again 6 valence electrons plus 6 times 7. That's 48 total. And the only way we're going to get this is by doing single bonds to everything around the sulfur. And you get this structure here, where clearly the sulfur has 12 around them, so it's definitely going beyond the octet rule, but that's okay because sulfur is in period 3. So 6 bonds on the S, 12 electrons on the S, but it's all good. You might ask why we can do expanded octets, and remember when I said hydrogen only wants 2? Because it has s orbitals, and the s orbital can only hold 2 electrons. Remember period 3, even though we don't start filling the d orbitals until period 4, period 3 can have d orbitals. So they exist even if they're empty, and we can use that space to help us make these bonds with the expanded octet. Occasionally, we get molecules with less than an octet. Usually this is observed with group 2 and group 3. However, a lot of the stuff that we see in group 2 in this class is going to be ionic, so you don't actually even have to worry about that one. We'll mainly just worry about one group 3 element, and that's going to be boron. So if we draw the Lewis structure for BF3, we can get these 2 structures. If we look at the formal charge, boron is in group 3A, so it has 3 valence electrons. So here it would have a formal charge of 0, and all these fluorines would be 0. Whereas in this case, it would have a formal charge of -1. This fluorine would be +1, and these would both be 0. Remember, a +1 on fluorine is super duper bad, so it's much better for boron to actually not even have its full octet. This is common with boron and halogens. So this is the only exception you need to know for molecules with less than an octet in this class. So if you see a boron, be careful and make sure you check the formal charge. Next, we'll talk about resonance structures. So I'll show you the Lewis structure for NO3- and its formal charges. If you go through, you get something that looks like this. So NO3- should have an overall -1 charge, so we're good there. We have these two oxygens with a minus and the nitrogen with a plus. The minus is on the more electronegative atom. This isn't a bad structure for nitrate. However, we can ask that double bond, does it have to go to that oxygen up top? It would be just as good if it went to that oxygen or this oxygen. And if that's the case, we can actually say the double bond can be shared between all of those oxygens. And this is what we call a resonance structure. So to indicate this, you actually have to draw all three of the Lewis structures and show resonance with this double-headed arrow. These three resonance structures all have the same formal charge, they're all equally good, and so they're actually all going to count for the Lewis structure. Again, for something with resonance structures, usually you actually have to draw all of them to correctly represent the molecule. So these are all equivalent, but we have to ask what this actually means. Does it mean that this double bond is skipping around all over the place in the actual NO3? And not quite. Sometimes we'll write this as a structure like this, where we do dotted lines to show that some electrons are actually shared between all three of these oxygens and the nitrogen. So what we observe is actually a blend of these structures. The easiest way to discuss this is to talk about bond order and bond length. So for a Lewis structure, the bond order is normally just the number of bonds. So the way this one's written, this is a single bond, that would be a bond order of 1. A double bond is a bond order of 2. A triple bond is a bond order of 3, etc. So if this case were actually true, we'd expect to measure a bond order of 2 on one oxygen and a bond order of 1 on two oxygens. But for resonance structures, what we actually observe is the total of bonds divided by the bonded atoms in the resonance. So for this structure, we have 4 bonds, 1, 2, 3, 4, shared between 3 bonded atoms. And so the bond order for this would be 4 divided by 3. So how do we observe bond order? Well, bonds with a higher order are going to be shorter bonds. So in this case, the bond length for NO3, all of the nitrogen-oxygen bonds are observed to be the same length. And that length is somewhere in between a single bond and a double bond. So with that in mind, let's look at the structure of NO2-. And we can compare that to NO3- and think if it would have a higher or lower bond order and a shorter or longer bond length. And the answer for this is higher and shorter. There's just 2 bonded atoms and 3 bonds, so this would be 3 bonds divided by 2. So it has a bond order of 3/2, which is greater than 4/3. And remember, a higher bond order means a shorter bond length.